Welcome back. We are solving the problems from chapter number 4 and level 2 student workbook problems. I think we covered problem number 3 in the last session. Now let's solve problem number 4. Problem number 4. Consider the following circuit using ideal op amp. The IV characteristics of the diode is described by the relation I is equal to I naught into e to the power of V by Vt minus 1, where Vt is equal to 25 millivolt, comma, I naught is equal to 1 microampere, and V is voltage across the diode taken as positive for forward bias. That is what is our convention as well. The same thing is given. Okay. The problem is, problem number 4, problem is this is 100 kilo ohm and Vi is given, Vi is equal to minus 1 volt, and this is the PN junction diode. This is what your V naught, and this is 4K. Okay, this is what is given, and the current which is what is flowing through I is given. Current flowing through PN junction diode I is equal to I naught into e to the power of V by Vt minus 1. It is described like this. When I say this is what your PN junction diode, if the voltage across the PN junction diode is V and the current flowing through PN junction is I to V relationship is given, and where Vt is equal to 25 millivolt and I naught is equal to 1 microampere. If this is what is the case, asking for V naught. What is V naught? Okay, you can say option A 0 volt, option B 0.1 volt, option C 0.7 volt, option D 1.1 volt. Can anyone guess what could be the answer? Guess. Anyway, after solving the problem, we'll get the answer. Right? I am asking you to guess what could be the answer. Right? Maybe majority of you qualitatively, if you think, right, if diode is conducting, right, then negative feedback, then this is 0, then the voltage at this point with respect to ground is nothing but the voltage drop across 4K plus the voltage drop across PN junction diode. You may think that because when it is conducting, the PN junction diode is conducting, then it will have 0.7 volt plus something. Therefore, your V naught will be plus 0.7 plus something, because this is 0, because virtual current concept. Therefore, 0.7 plus something, 0.7 plus something, either C or D. Definitely 0.7 plus something, you may expect D. Maybe I am just asking you or guessing you. Sorry, I am asking you to guess. Therefore, you may get V naught is equal to 1.1, right? But let's see what we get, right? Before that, let me explain theoretically. What is the theory? Do you know the status of PN junction diode? Don't take it as minus 1. Let us say this is Vi. Now, to find the status of PN junction diode, right? Open the diode D. Open the diode. Wherever you have diode, to find the status of diode, immediately open the diode. Open the diode to find its status. To find its status. Right? When you open the diode, minus, plus, this is your, what are maybe some R, and this is Vi, okay. Then, when you open, this is your V naught, some resistor. Therefore, now bring back your diode, but don't connect it. Okay, this is what your diode D. Therefore, now let's see. If this is what is the scenario, right, it is open loop. Your op amp is in open loop. When op amp is in open loop, then can you apply virtual ground concept? No, because it is open loop. Then it is comparator. If diode is opened, to find the status of diode, your op amp is comparator. If op amp is comparator, tell me, if VI is positive, right? Now let's see, if VI is positive, case A, VI is positive, then let's see, if VI is positive, then what is the current which is what is flowing through R? Current entering into op amp 0. What is the current? It is floating, therefore no current. Therefore whatever VI, the same thing you will get here. This is VI and this is what is 0 volt. Therefore tell me if VI is positive. Therefore when VI is positive, which is more? This is 0, this is positive. Minus is more. When minus is more, your output will be minus VSAT or minus VCC. Let us say negative. Therefore now tell me, this is positive and this is negative. Tell me the status of PN junction diode. Your P is connected to negative, N is connected to positive. Therefore diode is in reverse bias. Your diode is off. If diode is off, remember your V0 is independent of Vi. Your V0 will be, that's what I am saying. If Vi is positive, your V0 will be plus VCC. That is what you will get. That's it. Okay. Now, case 2, that is nothing but Vi negative. When Vi is negative, okay. Remember, off means reverse bias. Okay. That is nothing but off only. Okay. Reverse bias. This is nothing but reverse bias. Now, when Vi is negative, then let me use different color. Therefore, this is negative. When this is negative, this is 0. Which is more? Plus is 0, minus is negative. Which is more? Plus is more than plus VCC, which is positive. Therefore, tell me this is negative, this is positive. Then tell me P is connected to positive, N is connected to negative. Your diode is in forward bias. Therefore, your diode is in forward bias. Because we should not say on and off. Why? Exact current equation is given. Means it is exact model, not even approximation 1, approximation 2, approximation 3. Right? We have to use exact equation. Therefore, either forward bias or reverse bias. That is what we need to say. Not, don't say on and off. When you say on and off, on means short circuit, off means open circuit. Like that. Okay. Now this is forward bias. When diode is in forward bias, there is a current which is what is flowing through it, depending upon the voltage across the PN junction diode. Right? How much current it needs to satisfy KCL, then to get that much current through PN junction diode, how much voltage it needs across the PN junction diode, that much voltage will be given by your op amp. Okay, to satisfy KCL and KVL. That is what we need to write. We will write and then we will solve. Therefore, now tell me what is your V0. If diode is forward bias, that is what we need to have. Therefore, now diode is conducting. When diode is conducting, therefore, virtual ground concept, negative feedback will come into picture. Right? Negative feedback op amp. When it is negative feedback op amp, then virtual ground concept is valid. Then virtual ground concept is valid. Virtual ground concept is valid. Okay. Then we need to solve the problem. Take it. Then we will see that is the reservoir. What is your input? We need to find V0 for what? For negative voltage only. He has given it. Problem statement itself asking V0 for Vi is equal minus 1. Therefore, only for Vi negative, your diode is in forward bias, then only negative feedback, virtual ground concept, nodal analysis, you will get the answer. That is what we need to do. Therefore, before solving the problem, we got to know for what values of input your diode will be in forward bias. That is what we got it. Okay. Take it. And the problem is also related to negative values of input. Over? Okay. Now let's find the output. Can I erase this? Yes. Now, therefore, for the negative values, therefore let us apply Marshall concept. Let us say this is what is voltage across the PN junction diode, V. Then the current which is what is flowing through PN junction diode, that is nothing but I. And the relation between I to V is nothing but is already given. Okay. Now, apply nodal analysis. If you apply nodal analysis, because Marshall concept is valid only for when Vi is negative, therefore what is the voltage now? This is what is 0 volt. Okay. Now, tell me. Current leaving from this node, which is nothing but what? 0 minus Vi. What is Vi? Minus 1 divided by 100k. Right? Plus current leaving from this node. Tell me what is the current which is leaving from this node? 0 minus V0 divided by, we don't know the resistance, forward resistance of your diode, and 4k. Directly can I say the current which is flowing through PN junction, you know already, therefore can I say the current leaving from this node is nothing but minus I. Minus I is equal to 0. If you take this to right hand side, what is I? I is equal to 1 by 100k. 1 by 100k. You take this as equation 1. And we know that what is I? I is equal to I0 into e to the power of V by Vt minus 1, right? Therefore, you equate, this is what is equation 2, 1 and 2, therefore 1 by 100k is equal to, what is I0? I0 is already given, which is nothing but what? 1 micro, therefore 1 micro into e to the power of V by Vt, Vt is already given, minus 1. Okay, now this 100k if you multiply here, this is nothing but what? 100k into 1 micro, 10 to the power of 5 into 10 to the power minus 6, 0.1, right? 1 by 10, then it will become 10. Therefore, e to the power of V by Vt minus 1 is equal to 10. Right? Then what is e to the power of V by Vt? E to the power of V by Vt is equal to 11. Then what is V? V is equal to Vt ln 11. That is what is the voltage across the PN junction diode. Once you get this, right, then tell me what is your output KVL, right? This is what your KVL. Therefore, output KVL. What is output KVL? Voltage at this point with respect to ground is nothing but 0 only. Therefore, V0 to 0. V0 is equal to the drop across this, that is nothing but I into 4k plus the drop across the PN junction, that is what is V, which we already got, which is nothing but Vt ln 11, right? So what is I? I is already known to you, which is 1 by 100k into 4k plus V. Therefore, kk will be cancelled, 1 by 25. Therefore, this is 1 by 25 plus V, right? What is 1 by 25? 40 millivolt, okay? 40 milli plus V. Then now we need to solve what is voltage across PN junction diode. Therefore, what is voltage across PN junction diode? Vt. Vt is nothing but, if you solve you will get it, 25 milli into ln 11. This is nothing but natural logarithm, which is what is base E. Using your calculator, if you calculate, you will get it around 59 point something, you can say 60 millivolt, right? Therefore, you can call this as equation 3. Then 3 implies, therefore, what is V0? V0 is equal to 40 milli plus 60 milli. This is from 3. From 3. Therefore, this is nothing but 100 milli, which is nothing but 0.1 volt. What did you expect? I think before solving the problem, we expected something. What is it? We thought when this is conducting 0.7 plus something, you may get 1.1. But you know what we are getting? 0.1. What does it mean? Tell me what is the current which is what is flowing through PN junction diode? That is nothing but what? 1 by 100k. What is 1 by 100k? 10 microampere. To flow current of 10 microampere through forward bias PN junction diode, How much is the voltage which is what is required? The voltage requirement is 60 millivolt. If the volt exact model, it's not approximation 1, approximation 2, approximation 3. It is exact model. Therefore, if you take exact model, if you take VI characteristics, this is V, this is I, right? Then up to V gamma current is not significant. After V gamma current is significant. You know, I used to say that the current will be in the order of milliampere. That is what your forward bias current. And the reverse saturation current, this is nothing but your I naught. This is nothing but your I naught. Your I naught is 1 microampere, that is given. Now, to get the current, this current will be in the order of microamperes. And this is what your V gamma, right? This is your V gamma. After V gamma, current will be in the order of microampere. But you know, what do you need? Actually, the current, if you see the KCL, I'll give you time to write down. If you see the KCL, right, this is nothing but the current, 0 minus. Therefore, current is flowing like this. Therefore, the current, which is nothing but 10 microampere. If you observe clearly now, this is nothing but 10 microampere. 10 microampere. That current has to come from where? Op amp input, it will not give any current, it will not take any current. That has to come from the PN junction diode. Therefore, who is giving that current? Therefore, the current through PN junction diode in series current is constant. Whatever voltage you are getting from the op amp output, right? That voltage is equal to this voltage plus this voltage. The amount of voltage which is what is applied across PN junction diode, such that the current which is what is flowing through PN junction diode should be 10 microampere. Therefore, in series current is constant, the current is coming from your op amp, flowing through and then giving you and then satisfying. KCL is satisfied, KVL should be satisfied. And if you take PN junction diode standalone, to get a current of 10 microampere, but typically when PN junction diode is in forward bias, the current will be in the order of milliampere. But for that we need to have the voltage across the PN junction diode should be greater than or equal to V gamma, right? But we don't want the current, we don't want current through PN junction diode in the order of milliampere, we want only 10 microampere. To get a 10 microampere of current through PN junction diode, forward bias PN junction diode, how much is the forward bias voltage? That is very minimum, approximately equal to 0, but less than V gamma, very much less than V gamma. Actually, that is what we got. Therefore, we got that is 60 millivolt. When the forward bias voltage across the PN junction is 60 millivolt, you'll get the current in the order of 10 microampere. Yes, satisfied. Therefore, ultimately KCL and then KVL. Okay. Therefore, what is the answer? Answer is D. Sorry. Answer is B. 0.1 volt, not 1.1. I'll give you 2 minutes time. Try to write in 2 minutes. Then we'll solve problem number 5. See whether these problems are level 2 problems, right? Remember, if you follow the methodology or procedure, you'll get the answer. Okay? We should not take few things as granted. Okay? We can take, provided some condition is true. Here, diode is in forward bias. Don't think that if diode is in forward bias, always the voltage across the PN junction will be 0.7. No. The voltage is applied like 60 millivolt, whatever current. That depends on KCL, KVL. Okay? Let me get some water. 30 more seconds. After that we will see problem number 5. Problem number 5 is interesting. Okay, let's see. Done? Okay. Problem number 5. For the circuit shown in figure, the capacitor C is initially uncharged. At a time t is equal to 0, switch is closed. The voltage Vc across the capacitor at a time t is equal to 1 millisecond is. C is equal to 1 microfarad and switch is closed at a time t is equal to 0. Okay. Then in the figure shown above, the op amp is supplied with plus or minus 15, right? Therefore this is having plus 15 and minus 15. Now asking for what is Vc at time t is equal to 1 millisecond. Okay. Option A 0, option B 6.3 volt, option C 9.45 volt, option D 10 volt. Okay. Now listen, first of all, before closing the switch, right, see, if the problem is associated to a switch, we should identify the switch, the status of the circuit before closing the switch, then exactly at the time of switching and after closing the switch, right? Therefore let me analyze. T less than 0, switch is not closed, therefore switch is open. When switch is open, what is the circuit? This is what is your circuit, minus, plus, right? Now this is what is our, now this is what is having 10 volts, just writing equivalently, and then this is what is our switch. Switch is open but the capacitor is there. Initially the voltage across the capacitor, right, that is 0. Therefore Vc is equal to 0, the initial voltage. It is not charged, it is uncharged, that is what is given. Okay. Now let us say this is what your voltage V0, output voltage. Okay. Now tell me, if switch is opened, okay, this is what your capacitor, right, having some capacitance, this is what your C. Tell me, negative feedback or positive feedback or open loop? No feedback, it is open loop, right? Therefore your op amp is in open loop. If op amp is in open loop, this is nothing but what? This is open loop op amp, therefore it is comparator. It is comparator. When I say comparator, it compares voltage between minus and plus, then based on that it will respond and then give you output voltage. Therefore now tell me, Which is more? What is the voltage? Don't apply virtual current concept. Don't say that this is 10, this is 10. No, we cannot say. It is comparator, no feedback. This is 10. Current entering into op amp, 0. There is no current entering into this branch because this is open. Now the current which is flowing through 1K, 0. Drop across 1K, 0. This 0 will come here. Therefore, 0 is coming here. Now tell me, this is 10, this is 0. Which one is more? Which one is more? Plus is more. Then what is your output? You'll get plus VCC. What is plus VCC? Which is already given 15 volt. Therefore, what is your V0? V0 is 15 volt. That is what is your voltage V0. Okay. And what is voltage across the capacitor? Don't say 15. Don't say 15. Maybe few of you may think that because this is 15, your capacitor voltage will be going to 15. No. One on the other end of the capacitor terminal is floating. If there is no current flowing through capacitor, capacitor cannot charge. Floating means current cannot flow. If current cannot flow, it cannot charge. It is floating only. Therefore, VC will be 0. The voltage across the capacitor will be 0. Don't say the node voltage at this point with respect to ground is 15. But the voltage at this point with respect to floating terminal is not 15. Floating terminal, we cannot say anything. Therefore, the voltage across the capacitor is 0. If it is initially uncharged, it will be uncharged only because there is no path, there is no current which is flowing through the capacitor. If there is no current, no charging, no voltage change. Therefore, whatever voltage you have, which is uncharged state, until current flows, that voltage will be 0. Don't say 15 because that is 15 with respect to ground. But this is not ground, this is floating. Very important point. I guess this is done. If this is over, now we got to know the status of the circuit, right? Now switch is closed at a time t is equal to 0. Therefore, let us start. Now switch is closed at a time t is equal to 0. Let me say switch is closed at a time t is equal to 0. Therefore, now I am speaking about t is equal to 0 plus. What do you mean by 0 plus? 0 plus is nothing but 0, but just after closing the switch. 0 plus is nothing but, let us say this is what your switch. T less than 0, switch is open. T greater than 0, switch is closed. Then what is t is equal to 0 or t is equal to 0 plus? T is equal to 0 plus is just before contacting the switch. That is 0 plus. What is 0 minus? Just before contacting the switch is 0 minus. Just after contacting the switch is 0 plus. 0 minus 0 plus both are 0 only. But just to differentiate with respect to contacting and not contacting just before and then just after, that is what people say 0 minus and then 0 plus. It is exactly time t is equal to 0 only, but just before, just after, which is instantaneous point. That is fine. Therefore, exactly time t is equal to 0 means plus means switch is closed. When switch is closed, right, at a time t is equal to 0 plus, now tell me. This is important, minus, plus, and this is what your resistor. This is 10K, sorry, 1K. If you go ahead with 10K, you'll get wrong answer. Okay, 1K, and now this is what is your 10 volt, right? Now switch is closed. When switch is closed, now the capacitor, right? Basically, this is nothing but what? Integrator, right? This is integrator. Okay, that's fine. Now I'm speaking time domain V0, right? For earlier, before closing this is what is your V0? Your V0 is nothing but V0 at t less than 0 before closing the switch. Okay. Now tell me, this is what is our voltage. This is what you see. Now this is what is voltage across the capacitor. Voltage across the capacitor cannot change instantaneously. Voltage across the capacitor cannot change instantaneously. Therefore, what is voltage across the capacitor? That is 0. Now this is also 0. At a time t is equal to 0 plus, even you close the switch, voltage across the capacitor cannot change instantaneously. What is VC? VC is equal to 0 volt at a time t is equal to 0 plus. Because voltage across the capacitor cannot change instantaneously. Therefore, now tell me, what type of feedback? Negative feedback, positive feedback, or open loop? Remember, the moment you close the switch, and what is this? This is 0. What does it mean? This is 0. Means there is a sampling from V0 to the negative point. Therefore, it is negative feedback. Therefore, now op amp is in negative feedback. The moment you close the switch, immediately there is a negative feedback. But at that time, the voltage across the capacitor is 0. Therefore, this is short circuit. What may be? This is negative feedback. If it is negative feedback, then virtual ground concept is valid. Virtual ground concept is valid. Virtual ground concept is valid. Right? If virtual ground concept is valid, what is virtual ground concept? We know the voltage at plus. What is that? 10. Then what is this voltage? Now the voltage is 10 only. That is what is your virtual ground concept. Right? Now very important point. Therefore tell me, therefore we applied, this is negative feedback, virtual ground concept is valid. Now this is what is 10 volt. Right? Now T greater than 0 plus. T greater than 0 plus. T greater than 0 plus. I can say greater than 0. This is case 1. This is case 2. Now this is case 3. Right? Now, see, but one more point. Let's see KCL. What is KVL? KVL is nothing but what? Then what is your V0? The voltage across the capacitor is 0. Then you know what will happen? Immediately the moment you close the switch, whatever 15 volt you have, that 15 volt will become 10 at time t is equal to 0 plus. The 15 volt whatever you have before closing the switch, the moment you close the switch it will be 10. Why? Voltage across the capacitor is 0. That cannot change instantaneously. Whatever you have, you had 0, the same thing will be there at a time t is equal to 0 plus. But to satisfy KVL, because we know the voltage at this point is nothing but 10 because of virtual current concept, because it is a negative feedback, then the same 10 will come here because the drop across the capacitor is 0, then the same 10 is coming here. Therefore suddenly 15 volt will become 10 volt, but the capacitor is 0. Now tell me, this is 10, there is a current, right? Right, there is a current. Therefore tell me what is the current? 10 minus 0 divided by 1k, that is nothing but 10 milliampere. Therefore that 10 milliampere current is flowing like this. When 10 milliampere of current is flowing through this, tell me from where you are getting that current? Op amp input cannot give the current. That has to come from this. Therefore, your op amp should give the current of 10 milliampere that has to flow through this 1k. Therefore, what is that current? That is constant. If virtual ground concept is valid, it is always 10. If this is always 10, this is always 10 milliampere. The 10 milliampere is always coming from the capacitor. Therefore, the current which is flowing through the capacitor is always constant, which is 10 milliampere. If constant current is flowing through the capacitor, you will get the voltage which is increasing ramp. Therefore, the voltage across the capacitor now will increase. It will increase like a ramp because constant current is flowing through the capacitor. I hope everybody understood. Right? Now, therefore, T greater than 0 plus, then constant current. Therefore, constant current which is nothing but I is equal to 10 milliampere is flowing through capacitor. Is flowing through capacitor. Is flowing through capacitor. Okay. Therefore, what is your circuit? Now, if you see your circuit, this is nothing but minus plus. See, I am going step by step. Now, this is what your capacitor. Right? Now this is your output voltage. What is your output voltage? Your output voltage is 10 volts. This is what your 10 volt. Now this is also 10 volt. This is 10 volt and this is ground. This is 1k. Right? Now we need to find the voltage across the capacitor. Right? Therefore, this is what is 10 volts. This is 10 volt and this is 10 milliampere. The same current is flowing through this, right? The current which is what is flowing through this. This is also 10 milliampere because the same current is coming and then going like this. Therefore, now tell me, what is your V0? Now V0 is not 10 exactly. What is your V0? Now KVL. If you apply KVL, what is V0? V0 is equal to voltage across the capacitor Vc plus the voltage at this node, that is 10. Vc plus 10. That is what is your voltage. At a time t is equal to 0 plus, what is voltage across the capacitor? 0. Therefore, 0 plus 10, that is what is 10. But now, as the voltage across the capacitor, because as the current is flowing through it, the voltage across the capacitor is increasing linearly. As the voltage across the capacitor is increasing linearly, Vc is increasing. When Vc is increasing, then your V0 is also increasing because V0 with respect to ground is nothing but voltage across the capacitor plus voltage at this point with respect to ground, which is 10. Therefore, that is what it is. Okay. Therefore, now tell me, we want to know what is voltage across the capacitor. The moment you close the switch at a time t is equal to 1 millisecond, what is voltage across the capacitor? That is what is asking. Okay, now tell me. Therefore, tell me, we know that what is voltage across the capacitor? 1 by C integral I dt. We know I is constant, which is 10 milliampere. Therefore, I by C into T. Right? Therefore, this is what is your voltage across the capacitor. Now, a point. If you substitute T is equal to 1 millisecond, right? Therefore, at a time T is equal to 1 millisecond, if you substitute what is voltage across the capacitor, which is nothing but what is I? 10 milli. What is the capacitance value? Which is 1 micro, and into, if you take T is equal to 1 millisecond, this is 1 milli, milli into milli, micro will be cancelled, Vc is equal to 10 volt. Therefore, what is voltage across the capacitor? If you say 10 volt. But tell me, if Vc is equal to 10 volt, if Vc is equal to 10 volt, then what is your V0? Your V0 will be Vc plus 10, which is 20. It cannot be 20. Your output voltage cannot be 20. Why output voltage cannot be 20? Because the maximum output voltage what you can get is nothing but what? Is 15 only. Therefore, you know what will happen? As the voltage across the capacitor is increasing, let us say this is what is voltage across the capacitor, and this is what is your output voltage. This is what is time t. Therefore, timing diagrams are very important. Vc, and now this is V0. Just listen. This is what your time t is equal to 0. Therefore, initially what is voltage across the capacitor? 0. Then initially what is voltage across the t less than 0? We have 15. Sorry, the 15 became immediately 10. Therefore, let us say this is what is 15. 15 became suddenly 10. Therefore, now this is what is 10. Right? This is what is your 10. This is what is your 15 volt. 15 volt became suddenly 10. Let us say this is what is 10 volt. At a time t is equal to 0, and voltage across the capacitor. Now capacitor is charging linearly. As the capacitor is charging linearly, right? As the capacitor is charging linearly, right? What is your output voltage? Your output voltage is equal to Vc plus 10. If Vc is increasing linearly, your V0 is also increasing linearly from 10. It reaches till 15. When it reaches to 15 means what? For what voltage of capacitor? For when Vc, voltage across the capacitor is 5 volt, then this is 5 plus 10, 15. Once the V0 is reaching to 15, remember, once the V0 is reaching to 15, then it cannot cross more than that. It cannot cross more than that. What does it mean? Because maximum voltage what you can get at the output is nothing but what? That is nothing but 15 only. Therefore, it went to maximum voltage. Then nothing. It cannot supply the current to see this. Then you know what will happen? Then it entered into, it is like your capacitor will be kind of open circuit. There is no current which is what is flowing through it. If capacitor is like open circuit, then you know what will happen? From this point onwards, your capacitor is trying to charge to what? Therefore, now this 10 volt won't be there. This 10 volt won't be there. Then 2, because it cannot pass current of 10 milliampere. Then slowly, you know, it is like open circuit. Then your capacitor will be finally charging to the 15 volt what you have. Therefore, your capacitor is trying to charge exponentially from this point to reach 15 volt. But your output voltage will be 15 volt only. Therefore, at what time your voltage across the capacitor will be 5 volt? Can anyone tell? For what voltage? This is what is voltage across the capacitor. Okay. See, this is not straightforward. It may confuse you, but it's fine. If you go step by step, you will get it. Okay. Now, if I say, tell me for what time, right? To find time t, let us say this is what is time t1. This is what is time t1. Let us say somewhere we want to find, okay, this is what is 1 millisecond. We want to find that 1 millisecond, what it may be. Therefore, now tell me to find t1, at which voltage across the capacitor is 5 volt. Therefore, according to that, 1 implies 5 is equal to I by C. I is nothing but 10 milli divided by C is nothing but 1 micro into time t, that is nothing but t1. Therefore, what is t1? t1 is equal to 5 micro divided by 10 milli. It will become, milli will become kilo, then become 0.5 millisecond. Therefore, it is what is becoming 0.5 millisecond. Till 0.5 millisecond, right? This T1 is 0.5 millisecond. But if you want to know still another 0.5 millisecond, what will be voltage across the capacitor? Because your capacitor is trying to charge too. Once V0 is reaching to 15, right? Now, I don't have space, okay? I don't have space. Actually, I need to write it. That is case 3, right? Now, case 4. T greater than T1, which is nothing but 0.5 millisecond. Then I need to explain. Okay? Take it. I'll rub it, then I'll explain. Or approximately by seeing this waveform, we can say linearly and non-linear. Therefore, you can take voltage across the capacitor and you can substitute. Even then, you'll get the answer, but not accurate, very accurate answer. If you want approximate answer, you can just take it like this is V0 will be like 15 and then capacitor will be charging to it, then you'll get it. Okay. Almost you'll get same answer. Even if you consider voltage across the capacitor, the formula and the time constant into R into C, you'll get the answer. But I'm explaining with respect to virtual grid concept, and then what will happen initially, it will be faster, later on it will become very slow. The timing diagrams are important. Once your op-amp output reaches 15, it stays at 15 because it cannot cross more than 15. But if you use directly this formula, you'll get 20, which is not correct. Then if you substitute this, you may get 10, but 10 is also there. Options are there, right? Yeah, 10 is also there, but that is not correct. After this, the case 3, that is what is the continuation part. Okay. Done? See, while noting it down, try to understand and then write down. Don't copy it blindly, okay? If you copy it blindly, you cannot solve the problems anytime on your own. Once you understand the procedure, you try to solve on your own, then you'll get it. And you'll remember the procedure as well. Think last step, then with that I can say we can get the answer. The last step is nothing but t greater than, case 3, t greater than 0, we have seen this case. Now from now t greater than t1 till 1 millisecond, because the problem is asked to find what is voltage across the capacitor at 1 millisecond. Okay. And the time is almost over. I'll continue in the next session. You try to think and then try to solve, okay, before watching the second, or I can say the next session, where we will see the complete solution. Therefore part 3, right? Part 4, t greater than 1 millisecond, sorry, 0.5 millisecond, or t greater than t1, which is 0.5 millisecond. Okay. I'll continue in the next session. We will see that. Try to solve on your own the point number 4 and then try to find the voltage across the capacitor exactly at time t is equal to 1 millisecond. But under steady state, remember, the voltage across the capacitor will go to 15 volt. The voltage across the capacitor will go to 15 volt, whatever you have here. But asking at time t is equal to 1 millisecond. Okay. Thank you.